We now see the two approaches to calculate definite integral. The first is definite integral calculated as a limit of sum, and second approach is to use the fundamental theorem of calculus. Now let's go over this one by one. Firstly, let us see how we can calculate the definite integral as the limit of sum. Let's understand what this limit is or what this sum is. So for that, first of all, let us consider the graph of some arbitrary function denoted like this. Let's call the function as, say, f of x. Now we want to calculate the area between two limits on x. Let's call those limits as, say, a and b. Right? Now to calculate the area under this curve, let us start by some approximation. That is, what do we do is, let us divide the interval between a and b into 4 equal parts to start with. So let's call that n as 4, which is the number of parts into which I am dividing that interval. Now corresponding to these markings, let us draw the vertical lines as shown here. So you see that the region is now broken into 4 different pieces. Now what do we do is, pertaining to each of this particular sub-region, if we consider the right hand side boundary of each region, then taking that as the length, we can complete the rectangles as shown here. That is, we will have to extend the left side slightly above, and then once it reaches at the same level as the right hand side boundary, we draw a horizontal line to complete a rectangle. Right? Now let us call the width of each rectangle as, say, h. Okay? So for the end of the first region, we have the x coordinate as a plus h. Then next we would have a plus 2h. Then we will have a plus 3h. And finally, of course, b will be nothing but a plus 4h, simply because we are dividing the region into 4 parts. Right? So if we want to calculate the area of all the 4 rectangles, that gives us a fairly good approximation of the actual area that we want to calculate, isn't it? So let me call that particular area as, say, a4, right? Or if we want, we can denote it as, say, am, where currently we are considering n as equal to 4. So what does this mean is, this is the area of all the 4 rectangles added. Now if you look at the first rectangle here, we want to find out what is the length of that particular rectangle, isn't it? So for that, let us concentrate on this particular point. If you observe, its x coordinate is a plus h, isn't it? So therefore x coordinate is a plus h, and the y coordinate will be given by the expression of the function. So therefore that will be nothing but f of a plus h. Right? So that's the x and y coordinate pair of that particular point. So therefore the length of the first rectangle, that is a vertical height, we may say, is nothing but f of a plus h, and the width is nothing but h, as we have already seen. So therefore its area will be nothing but h into f of a plus h. So that's the area of the first rectangle. Plus, for the second rectangle, the width is still same, that is h, but now if we consider the height, that will now be f of a plus 2h, because the x coordinate is now a plus 2h. So continuing in this manner, okay, we will have the last rectangle with the area as h into f of a plus 4h. So now this is the case when we have n equal to 4, that is 4 subdivisions, isn't it? Now what happens, suppose instead of 4, suppose we increase the divisions, that is we make it as 8 divisions, then it will have slightly better approximation, because as you can imagine, suppose let us consider the further subdivisions. Now if I want to show the rectangles in green, the topmost boundaries of the rectangles in green, so you see that the extra or the surplus area that we are counting above the required area is less than the previous case in which we had considered only 4 rectangles, isn't it? So now if you see, the more number of rectangles we consider, better is our approximation and closer is the calculation of area. So therefore we can take now the limit of this particular sum of areas as n becomes larger and larger and tends to infinity, isn't it? So therefore we finally write that the actual area, so by actual area we mean the required area under the curve. So actual area under the curve is nothing but the limit of what? The sum of all the areas of n rectangles. So therefore to consider the sum, we write the summation sign, isn't it? Now we have to sum up the area of all the rectangles, and for individual rectangle the area is given by h into f of a plus. Now here we will have to put some counter, because this r will vary from 1 to n. As you can see here, it is a plus 1h, a plus 2h, a plus 3h and a plus 4h. So if we are talking about n rectangles, then the r must vary from 1 to n, and we are taking the limit as this n itself becomes bigger and bigger and approaches infinity, isn't it? So therefore that's the way to calculate the area under the curve. Now of course we can bring the h outside the summation because it is not dependent on r, so therefore this we can write as h is summation of f of a plus rh, where r varies from 1 to n. So therefore this is the final formula to calculate the area under the curve, which is nothing but the definite integral as the limit of this particular sum. Now this definite integral is technically denoted in this symbol, that is, this is the integration sign. We want to integrate f of x, which is the function, with respect to x, but now we additionally specify the lower and upper limits, which are a and b respectively. So therefore the value of definite integral is nothing but the limit as shown here. Now in the example we would be typically given what is the lower limit a and what is the upper limit b, and based on that we can calculate the required definite integral. Now we will solve few sums based on this process.